In a heavily guarded test facility outside Shenyang on November 7, 1987, a jet engine that had consumed 4 years of research and hundreds of millions of yuan suddenly began disintegrating at full afterburner, its turbine blades glowing white-hot before fragmenting and tearing through the containment housing with enough force to kill test engineer Wu Danian instantly and critically injure 2 others. The engine, China's desperate attempt to reverse engineer the cooling systems of the American F100 turbofan that powered the F-15 and F-16 fighters, had just failed catastrophically, revealing that sophisticated metallurgy and thermal management systems cannot simply be copied without decades of accumulated materials science knowledge. As alarm shrieked and flames engulfed the test cell, Chief Engineer Zhang Weiguo realized that his country's aviation industry had reached the limits of what reverse engineering could achieve. This is the story of China's 7-year struggle to master engine cooling technology and the harsh lessons learned when ambition collided with the unforgiving physics of thermodynamics.
The engine that defined fourth-generation fighters. The Pratt & Whitney F100 turbofan engine represented a quantum leap in jet propulsion technology when it entered service in 1972. Designed to power the revolutionary F-15 Eagle air superiority fighter, it produced thrust levels that would have been considered impossible just a decade earlier, approximately 25,000 pounds of thrust with afterburner, generated by an engine weighing less than 3,400 pounds. This extraordinary power-to-weight ratio was achieved through advanced metallurgy, sophisticated cooling systems, and precision manufacturing that pushed the boundaries of what was technically possible in the early 1970s. The F-100's performance came from operating at temperatures that would destroy conventional engine materials. The combustion chamber reached temperatures exceeding 3,000 degrees Fahrenheit, while the high-pressure turbine blades, the components that extracted energy from the hot exhaust gases, operated in gas streams approaching 2,500 degrees Fahrenheit. These temperatures exceeded the melting point of the nickel-based superalloys from which the blades were manufactured, making sophisticated cooling systems absolutely essential for engine survival. The cooling technology employed in the F-100 was extraordinarily complex. The turbine blades were hollow, with intricate internal passages through which compressed air from the engine's compressor section flowed, carrying heat away from the blade's surface. These cooling passages weren't simple tubes. They were elaborate three-dimensional labyrinths with precisely positioned channels, impingement jets, and film cooling holes that created protective layers of cooler air over the blade's external surface. The geometry of these cooling passages had been optimized through years of research, computational modeling, and extensive testing. Manufacturing these blades required technologies that represented the cutting edge of American industrial capability. The blades were created using precision investment casting, where ceramic molds with intricate internal cores produced the complex internal cooling passages. The cores were positioned with extreme precision. Variations of even a few thousandths of an inch could compromise cooling effectiveness and lead to blade failure. After casting, the blades underwent specialized coatings, thermal barrier coatings that provided additional insulation from the hot gases, and protective coatings that resisted oxidation and corrosion at extreme temperatures. By the early 1980s, when China obtained access to F-100 engines through various means, the engine had matured into a remarkably reliable power plant. The F-100 PW220 variant had addressed early reliability issues through improved cooling, better materials, and refined manufacturing processes. American F-15s and F-16s, powered by F-100 engines, were demonstrating capabilities that Chinese fighters couldn't match: higher thrust-to-weight ratios, better sustained turn rates, superior acceleration, and the ability to operate reliably across a wide range of conditions. For Chinese aviation planners, this performance gap was deeply troubling. China's indigenous jet engines, primarily derivatives of Soviet designs from the 1950s and 1960s, were generations behind American technology. The most advanced Chinese engine in production, the WP-7, was essentially a copy of the Soviet R-11 engine that dated to 1953. Chinese fighters were consistently outperformed by American aircraft, and the gap was widening as the United States fielded increasingly sophisticated fourth-generation fighters.
The opportunity and the challenge. The opportunity to study F-100 engines came through multiple channels in the early 1980s. Pakistan, which operated F-16 fighters powered by F-100 engines, maintained relationships with China that occasionally provided access to Western technology. More significantly, Iran, which had purchased F-14 Tomcats powered by related TF-30 engines before the 1979 revolution, subsequently found itself unable to obtain spare parts or support from the United States and turned to China for assistance with engine maintenance and repair. Through these channels, Chinese engineers gained access to actual F-100 and related engines for detailed study. The project to reverse engineer F-100 cooling systems was formally initiated in March 1983 at the Shenyang Aero Engine Research Institute, one of China's premier aviation engine research facilities. The institute's director was General Liu Dapeng, a 61-year-old aviation engineer who had worked on jet engine development since the 1950s. Liu understood both the enormous potential benefits of mastering advanced cooling technology and the profound technical challenges involved. The technical lead was assigned to Chief Engineer Zhao Guo, a 44-year-old propulsion specialist who had studied at the Beijing University of Aeronautics and Astronautics before joining Shenyang Institute in 1965. Zhang had worked on various engine projects throughout his career, primarily involving modifications and improvements to Soviet-derived designs. He was experienced, technically sophisticated, and increasingly aware of how far Chinese metallurgy and manufacturing capabilities lagged behind American standards. When Zhang first examined an F-100 turbine blade in the Institute's secure examination facility in April 1983, he experienced both fascination and concern. The blade was approximately 4 inches long, with a complex airfoil shape optimized for extracting maximum energy from the gas flow. But what truly amazed him was what he saw when the blade was sectioned for internal examination. The intricate cooling passages that ran through the blade's interior like a three-dimensional maze. "Look at this complexity," Zhang told his deputy, Dr. Chen Minghua, a materials scientist who specialized in high-temperature alloys. "These cooling passages branch and reconnect in 3 dimensions. There are impingement jets here directing cooling air at specific hotspots. These holes along the trailing edge create film cooling. The passage geometry varies along the blade's length, presumably optimized for the local heat loads. This represents decades of research and development." Chen examined the sectioned blade under a microscope, noting additional details. The surface has multiple coating layers, probably a bond coat, then ceramic thermal barrier coating. The base metal is a nickel-based superalloy, very advanced composition. And look at the grain structure. This appears to be directionally solidified, possibly even single crystal casting. These technologies are far beyond our current capabilities.
The materials science gap. Dr. Chen Minghua took responsibility for analyzing the materials and manufacturing processes used in the F-100's turbine blades. This analysis revealed challenges that were even more daunting than the geometric complexity of the cooling passages. The blade material was a sophisticated nickel-based superalloy, likely PWA 1484 or a similar composition, containing precisely controlled amounts of nickel, chromium, cobalt, aluminum, titanium, tantalum, and other elements. These alloying elements were not randomly chosen. Each served specific purposes in providing high-temperature strength, oxidation resistance, and resistance to creep.
the gradual deformation that occurs in metals under sustained high-temperature stress. The alloy composition is critical, Chen explained to Zhang during a technical review in May 1983. The aluminum and titanium form intermetallic precipitates that strengthen the alloy at high temperatures. The chromium provides oxidation resistance. The tantalum and other refractory elements increase high-temperature strength, but achieving the correct balance is extraordinarily difficult. Too much of one element can cause brittleness, too little reduces high-temperature capability, and all the elements must be uniformly distributed throughout the casting. Chinese superalloy production in 1983 was decades behind American capabilities. The nickel-based alloys used in Chinese jet engines were derived from Soviet formulations from the 1950s and 1960s, with much lower temperature capabilities. Chinese foundries struggled to achieve uniform composition and to control impurities that degraded high-temperature properties. The specialized melting and refining processes used in American superalloy production, vacuum induction melting, vacuum arc remelting, and powder metallurgy techniques were not available in Chinese facilities or were in very early developmental stages. The directional solidification and single crystal casting technologies represented an even more profound gap. Conventional casting produces random grain boundaries throughout the metal, and these boundaries become weak points at high temperatures. Directional solidification aligns the grains in the direction of primary stress, eliminating transverse grain boundaries and substantially improving high-temperature strength. Single crystal casting goes further, producing blades that are literally single metal crystals with no grain boundaries at all. We don't have the equipment or knowledge to produce single-crystal turbine blades, Chan admitted. The process requires extremely precise control of the solidification process, carefully controlled temperature gradients in specialized furnaces. The withdrawal rates from the molten metal must be precisely controlled. The process parameters have been optimized through years of research. We're probably 15 to 20 years behind in this technology. The coating systems presented additional challenges. The thermal barrier coatings applied to F100 turbine blades were sophisticated ceramic materials, typically yttria-stabilized zirconia, applied in specific thicknesses using plasma spray or other advanced deposition techniques. These coatings provided thermal insulation, reducing the metal temperature beneath them by several hundred degrees, but the coatings had to adhere reliably to the blade surface, had to accommodate thermal expansion differences between the ceramic and the metal substrate, and had to resist spalling, that is, flaking off during thermal cycling. We don't have plasma spray equipment capable of producing the required coating quality, Chen continued. Our coating adhesion is poor. The coatings tend to spall after relatively few thermal cycles. This technology also requires substantial development.
Manufacturing impossibilities. While Chen's team grappled with materials challenges, Zhang focused on the manufacturing aspects of replicating the F100's cooling systems. The precision investment casting process required to produce hollow turbine blades with internal cooling passages was technically possible in China, but the level of sophistication required for F100 equivalent blades was far beyond current capabilities. Investment casting of turbine blades required creating ceramic molds with internal cores that would define the cooling passages. The cores were made from materials that could withstand the molten metal temperature but could later be removed chemically, leaving the hollow passages. For simple cooling passages, this was straightforward. For the complex, three-dimensional cooling geometries in F100 blades, it was extraordinarily difficult. The core positioning is critical, explained master foundry specialist Wang Zhanghuo, who had spent 30 years casting turbine blades. The cores must be positioned within the ceramic mold to within thousandths of an inch. If the core shifts during mold assembly or casting, the cooling passage geometry is wrong and the blade will fail.
For simple straight passages, we can achieve adequate positioning. For these complex branching passages with multiple cores that must align precisely in 3 dimensions, our tooling and processes are inadequate. The process of removing the cores after casting was also problematic. American foundries used specialized chemical solutions that could dissolve the core material without attacking the blade material. Chinese foundries had less sophisticated core removal chemistry, which sometimes damaged the blade material or failed to completely remove core material from complex passages, blocking cooling flow. Even if manufacturing could produce blades with the correct internal geometry, inspecting them to verify quality was a major challenge. The cooling passages were internal and couldn't be directly observed after casting. American aerospace companies used sophisticated X-ray computed tomography, CT scanning, essentially medical CAT scan technology adapted for industrial use, to non-destructively image the internal passages and verify that they matched design specifications. Chinese facilities in 1983 had no such capability. Their inspection methods were limited to simpler X-ray techniques that could detect gross defects, but couldn't provide the 3-dimensional visualization needed to verify complex internal geometries. "We're essentially casting blind," Wang admitted to Zhang. "We can create molds with cores positioned where we think they should be, but we have no reliable way to verify that the actual cast blades have passages matching the design. Some blades will be good, others will have blocked passages or misaligned cores, and we won't know which is which until they fail during testing."
The test program began. Despite the mounting evidence of technical challenges, political pressure demanded progress. The Chinese aviation industry was under intense scrutiny to demonstrate capability improvements and reduce dependence on foreign technology. Engine development was particularly critical, as it represented perhaps the most significant technological gap between Chinese and Western military aviation. By late 1985, Zhong's team had developed a modified version of an existing Chinese engine, the WP-13, a derivative of the Soviet R-13, incorporating cooling systems inspired by F100 technology. The modifications included redesigned turbine blades with internal cooling passages, improved combustion chamber cooling, and various other thermal management enhancements. The goal was not to exactly replicate the F100, but to incorporate its cooling principles into a Chinese engine design to achieve higher operating temperatures and improved performance. The modified engine, designated WP-13F internally, incorporated turbine blades that attempted to approximate F100 cooling technology. The blades were cast using Chinese superalloys, the best available, though still inferior to American materials, with internal cooling passages that simplify the F100's complex geometry to something that Chinese foundries might be able to produce. The passages were straighter and less intricate than F100 passages, representing a compromise between what was desirable and what was achievable. The first complete WP-13F engine was assembled in March 1986 and underwent initial testing on a test stand at Shenyang. The test facility consisted of a heavily reinforced concrete cell where the engine could be mounted and run at various power settings while instrumented to measure thrust, fuel consumption, temperatures, and vibration characteristics. The test cell was designed to contain engine failures, a precaution that would prove tragically inadequate. Initial testing at low power settings proceeded without major problems. The engine started successfully, ran smoothly at idle, and responded properly to throttle inputs. When power was gradually increased to intermediate settings, around 60 to 70% of maximum thrust, the engine continued to function, though temperatures were running higher than predicted, and some vibration characteristics were concerning. The first attempt to run at full military power, maximum thrust without afterburner, occurred on April 15, 1986. As the throttle was advanced, engine temperatures climbed rapidly. The turbine gas temperature exceeded design limits, and unusual vibrations developed. The engine technician throttled back before reaching full power, preventing an emergency shutdown, but clearly demonstrating that the cooling system was inadequate for the intended operating conditions. The turbine inlet temperature is approximately 150 degrees Celsius higher than predicted, reported Dr. Li Hua, the test engineer who had been monitoring the engine's performance. The cooling system is not removing heat effectively. Either the cooling airflow is insufficient, or the passage geometry is not providing adequate cooling effectiveness, or both. We need to investigate and make modifications.
Iterations and deterioration. The period from mid-1986 through 1987 involved building and testing 6 more modified engines, each incorporating changes intended to address problems discovered in previous versions. The iterations revealed a pattern of diminishing returns. Early modifications produced modest improvements, but subsequent changes yielded smaller benefits and sometimes introduced new problems. The second engine incorporated larger cooling passages, attempting to increase cooling airflow. This provided some improvement in cooling effectiveness, but reduced the structural strength of the turbine blades, as more material was removed to create larger passages. During testing at high power, 2 blades experienced cracks that forced test termination. The third engine used a different superalloy composition, attempting to improve high-temperature strength. The new alloy was harder to cast, resulting in higher rates of casting defects. Of 12 blades cast, only 5 were acceptable for engine assembly, and even these showed imperfections that were concerning. The fourth engine incorporated modified cooling passage geometry, attempting to improve cooling effectiveness without removing too much blade material. The modified geometry was difficult to manufacture. The ceramic cores required for investment casting frequently broke during mold assembly, and the cast blades often had blocked or partially blocked cooling passages. By mid-1987, Zhang's team was struggling with a fundamental problem. They were trying to optimize a system without truly understanding the underlying principles. The F100's cooling system represented decades of American research into heat transfer, fluid dynamics, materials science, and manufacturing processes. Chinese engineers could observe the end result, the complex cooling passages and coating systems, but they lacked the deep theoretical and practical knowledge that had led to that specific design. "We're copying the form without understanding the function," Zhang admitted to Chen during a discouraging review meeting in August 1987. "We see cooling passages with specific geometries, but we don't fully understand why those geometries were chosen. We observe coating systems with particular compositions and thicknesses, but we don't know all the factors that determined those specifications. We're trying to reverse engineer not just hardware, but decades of accumulated knowledge." The political pressure was intensifying. Defense officials wanted to see dramatic performance improvements. Factory managers wanted to begin production of engines with enhanced capabilities. Everyone wanted results faster than the technical realities would permit.
The fatal test. The seventh engine, completed in October 1987, represented what Zhang's team believed was their best effort to date.
It incorporated all the lessons learned from previous failures, used the best superalloy castings they had been able to produce, and featured cooling passages that were a compromise between effectiveness and manufacturability. Preliminary testing at low and intermediate power settings had been promising, with temperatures and vibrations within acceptable ranges. A full power test was scheduled for November 7, 1987. The protocol called for gradually advancing the throttle to full military power, maintaining that power setting for 5 minutes while monitoring all engine parameters, then advancing to full afterburner if military power testing was successful. The afterburner test would last approximately 1 minute. The test engineer for this run was Wu Danian, a 36-year-old propulsion specialist who had worked on engine testing for 8 years. Wu was thorough and cautious, respected by colleagues for his careful attention to instrumentation and his insistence on following test protocols precisely. He was stationed in the control room adjacent to the test cell, monitoring engine parameters on a bank of instruments and recorders. Zhang observed from the control room along with several other engineers and a military observer from Beijing. As Wu advanced the throttle, the engine's roar increased in intensity, clearly audible even through the test cell's heavy sound insulation. The instruments showed thrust climbing toward the military power target of approximately 7,500 kilograms. The engine reached full military power and stabilized. Temperatures were elevated, but within limits that had been observed in previous tests. Vibration was slightly higher than ideal, but not alarming. Wu maintained the power setting, carefully scanning his instruments for any signs of problems. After 3 minutes at military power, with everything appearing stable, Wu began the afterburner sequence. He advanced the throttle past the military power detent into the afterburner range. The instrument showed afterburner ignition, and thrust began climbing rapidly as raw fuel was injected into the exhaust stream and ignited, producing an additional thrust boost. For approximately 8 seconds, the engine operated in full afterburner. Then, without warning, the turbine inlet temperature gauge spiked upward, climbing far past its maximum reading. Simultaneously, vibration levels surged to dangerous levels. Wu's hand was moving toward the emergency shutdown switch when the engine exploded. The turbine section disintegrated first. The turbine blades, unable to withstand the combination of extreme temperatures and centrifugal loads, began failing in rapid succession. Each blade failure sent fragments flying, striking other blades and causing cascading failures. Within a fraction of a second, the entire turbine section had transformed into a storm of metal fragments spinning at tremendous velocity. The test cell's containment housing was designed to contain relatively modest failures, individual blade releases, or bearing failures. It was not designed to contain the complete disintegration of the turbine section. Fragments penetrated the containment housing, tearing through the steel walls and entering the control room. Wu Danian was killed instantly when a turbine blade fragment, traveling at several hundred meters per second, penetrated the control room wall and struck him in the chest. 2 other engineers were critically injured by fragments and debris. Zhang was wounded by flying glass from shattered instrument panels, but survived. The military observer escaped serious injury by being positioned behind a structural column when the explosion occurred. The test cell was destroyed. The engine was completely demolished. Fragments were embedded in walls 20 meters from the test cell. The damage was so extensive that accident investigators would later struggle to determine the exact failure sequence.
Investigation and reckoning. The accident investigation consumed 3 months and involved dozens of engineers, metallurgists, and safety specialists. The analysis revealed a cascade of failures that began with inadequate cooling of the high-pressure turbine blades during afterburner operation.
The afterburner operation had increased turbine inlet temperatures beyond what the cooling system could handle. The Chinese manufactured superalloy blades, operating above their temperature limits, began experiencing rapid creep deformation. The blades stretched under centrifugal load, with their tips growing closer to the turbine case. Eventually, one blade tip made contact with the case, causing catastrophic vibration. The vibration, combined with the thermally weakened blade material, caused multiple blade failures in rapid succession. The investigation also revealed serious defects in several turbine blades that had not been detected before engine assembly. Metallurgical examination of blade fragments recovered from the test cell showed that some blades had partially blocked cooling passages, the result of incomplete core removal during the casting process. These blocked passages prevented adequate cooling airflow, causing those blades to run even hotter than the already elevated temperatures. The inspection processes had failed to detect these defects before the blades were assembled into the engine. We were testing an engine with known inadequate cooling systems made from materials with insufficient temperature capability, using blades with manufacturing defects we couldn't detect, the investigation report concluded. The failure was not a matter of if, but when. Zhang Weiguo was removed from the project leadership, though not formally punished. The investigation acknowledged that he had repeatedly raised concerns about technical risks and had recommended more conservative testing approaches. The political pressure for rapid progress had overridden his technical caution. The WP-13F project was terminated in January 1988. All remaining engines and components were placed in secure storage. The test facility was rebuilt, with substantially improved containment capabilities designed to survive even complete engine disintegration.
The long road to competence. The failed F100 cooling system project became a watershed moment in Chinese aviation engine development. It forced acknowledgement of uncomfortable truths about the limits of reverse engineering and the importance of fundamental research and development. In the aftermath, Chinese aviation authorities initiated long-term research programs focused on developing indigenous capabilities in critical technology areas: superalloy development and production, advanced casting techniques including directional solidification and single crystal casting, thermal barrier coatings, non-destructive inspection methods, and computational modeling of heat transfer and fluid dynamics in turbine cooling systems. These programs proceeded slowly, without the political pressure for rapid results that had plagued the WP-113F project. Chinese researchers collaborated with foreign institutions where possible, sent students to study advanced materials science and manufacturing engineering abroad, and invested in facilities and equipment needed to support sophisticated engine development. Progress was measured in decades rather than years. By the late 1990s, Chinese foundries were producing directionally solidified turbine blades with significantly improved high-temperature capabilities. By the mid-2000s, single crystal casting was being implemented in production engines. Advanced thermal barrier coatings, CT scanning for inspection, and sophisticated cooling designs gradually entered Chinese engine production. The Chinese engines that eventually incorporated F100-level cooling technology, engines like the WS-10 turbofan that powers current Chinese fighters, appeared in the 2000s, representing roughly 20 years of development from the initial failed attempt. These engines demonstrated that China had finally developed the material science, manufacturing capabilities, and accumulated knowledge needed to design and produce turbines operating at temperatures approaching American standards.
Lessons in physics and patience.
Zhang Weiguo continued working in engine development until his retirement in 2008, though he never again led major projects. He mentored younger engineers, always emphasizing lessons learned from the F100 cooling system failure. Advanced technology cannot be shortcutted through reverse engineering alone. The F100's cooling systems represented 40 years of American research into material science, heat transfer, and manufacturing. We thought we could copy the result in 4 years. We were wrong. Real technological capability requires building foundations, research infrastructure, skilled personnel, accumulated knowledge, manufacturing expertise. These foundations take decades to develop. Trying to skip ahead leads to failure and sometimes to tragedy. Wu Danian's widow received compensation and support from the government, though nothing could replace her husband or restore her children's father. Wu became one of the uncounted casualties of China's rapid modernization, not a soldier killed in combat, but an engineer killed pursuing technological advancement under conditions of inadequate preparation and excessive haste. The F100 engine itself continued in American service for decades, with improved variants powering F-15s and F-16s into the 21st century. More than 25,000 F100 engines have been produced, demonstrating remarkable reliability and longevity. The engine's success came not just from the brilliance of its design, but from the maturity of American aerospace industry. The materials suppliers, the manufacturing expertise, the quality control systems, and the accumulated institutional knowledge built over generations. The story of China's failed attempt to copy F100 cooling systems is ultimately about the difference between appearance and substance, between copying and understanding. The cooling passages could be observed and measured. The coating systems could be analyzed and approximated. But the deep knowledge that made those systems work, the understanding of why specific geometries were chosen, how materials behave under extreme conditions, what manufacturing processes produce reliable results, that knowledge could not be stolen or shortcut. It had to be earned through patient research, systematic development, and the willingness to accept that some achievements require walking the entire path, no matter how long that journey takes.